Okay, so this is where we ended on the last one. I just wanted to show you, I don't have a lot of room here, but we know that force, sometimes force is mass times gravity, right? So if we set it equal to the big gravitational constant times these two masses divided by the radius squared, okay, this distance between, if it was to go around, like in a circle, that would be the radius. That's why it's referring to it as the r. And then if you divided that by m, okay, to both sides, that cancels. And then that would cancel one of those masses, and you would be left with gravitational constant, times mass divided by radius squared. And that's equal to little g. So we are going to actually solve that in a couple of slides. So this is saying that the gravitational force between two human-sized objects is so small. Only when one of the objects is a planet-sized or larger does gravity become an important force. So this, again, is your gravitational, Newton's law of gravity. And sometimes they will write it as M, like with a uppercase M, and then they'll have another M for a lowercase m, because one of the masses is so much larger than the other. And of course the r is the radius. And that should equal around 9.8 meters per second squared. So the gravity of a force, and this is what we just solved before, so I should have waited until this slide, but that's just where we took force of gravity is equal to mass times gravity. So it was saying you have mass 1 and mass 2 over r squared, and then you just take mass times gravity, plug it in there, and solve for little g, which ends up being this right here. All right, now the figure shows the free body diagram of an object in a free fall near the surface of a planet, which would be that with net force is equal to the force of gravity. And so the acceleration of free fall is equal to the force of gravity divided by the mass. And assuming, gravity is straight down. All objects on the same planet, regardless of mass, have the same free fall acceleration, which I think I kind of showed one day with maybe like a ball of paper and a book. For the most part, that is definitely true, especially if it was like in a vacuum situation. Again, though, if you are experiencing any kind of air resistance or some sort of friction, it could cause a little bit of difference. Okay, so this is just a big slide that I want to prove gravity. So the average radius of Earth is equal to, and this should be in your ebook, this should be in your ebook on useful information. You should have things like the average radius of the Earth, the mass of the Earth, the mass of the moon, things like that. The mass of the Earth is equal to 5.98 times 10 to the 24th kilograms. And so earlier we were saying this, you've got, oops, hold on. I gotta figure out my pin here. There we go. Go back. All right. So we were saying that you have this gravitational constant times mass 1, mass 2 over r squared. And then we were saying, oh, well, the force of gravity is just mass times gravity is equal to the gravitational constant times mass 1, mass 2 over r squared. And if we solve for little g, then we just divide both sides by m, and we end up with this. All right, so now we just got to solve. So we've got our gravitational constant is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times the mass of the Earth. So, so that's 5.98 times 10 to the 24th kilograms divided by the radius of the Earth, which we said to be 6.37 times 10 to the 6th meters. But we got to square that. So lots of exponents. Easily something that could be messed up on a calculator. So just make sure that, you use that big E button, or some calculators have that times 10 to the button, or some of you guys have those crazy fancy calculators that can do all kinds of stuff for you. So anyway, when you solve this, you should get 9.83 meters per second squared. And they're saying that the 0.03 difference is due to the Earth's rotation. But approximately 9.8. And that does depend on, where you are on the Earth. At the poles, it's slightly different. So, why can't I go?